We are taking a look at solution concentration. This is where we deal with the math associated with solutions. Imagine right now you're thirsty. Your brother or sister says, "Hold on, I think we have some pink lemonade mix." Your brother or sister goes to the cabinet, gets it out, gets a pitcher, dumps some in, puts in water, and mixes it together. Doesn't read the package, pours you some, and you taste it and you're ready to spit it out. Well, probably one of two things happen. Either not enough mix, so it tastes essentially like water, or too much that it's too sweet. You need it just right. You've got to do, of course, is dump it, read the directions, and get the right mix of the pink lemonade crystals, which is your solute, and a certain amount of water, which is your solvent. Now, when your lemonade dissolves in the water, it's a solution. And now the solute plus the solvent gives us the solution. In this video, we are going to go over 3 different ways that you calculate or quantify the concentration of a solution. And here at reference table T, we might as well start here because this is where you're going to find your equations when you need them. Alrighty, percent comes up again, percent composition, part over the whole thing times 100. That's the generic equation. For solutions, we might have percent by mass or even percent by volume. If it's mass, it's going to be grams over grams. If it's volume, it's going to be milliliters over milliliters or liters over liters. Then we get to parts per million, or ppm for short. This setup is really part over whole, but now times a million instead of 100. This concentration calculation is used a lot in environmental studies because you're looking for little concentrations of things that are harmful in, for example, groundwater or in the air. You might even have to deal with parts per billion with environmental studies, but here we're dealing with parts per million, percent composition, and the last one, this one is used all the time in the laboratory. That is known as molarity. Moles of solute over liters of solution. Again, solution is solute plus solvent. Molarity, the symbol, we use a capital M for molarity. With this information in reference table T, we're going to go over each one of these calculations, and then we have some other practice to do to get us ready for solution concentration. We are taking the same information, the 330 grams of calcium chloride in 1 liter of solution, and we're going to calculate it 3 different ways. Now, 1 liter is 1,000 milliliters. The density of water is 1 gram per milliliter. That means we have in mass 1,000 grams. You'll notice also for A, B, and C, I've written out the formulas. Always, always, always. I don't care what math you're doing in chemistry, write the formula down before you plug the numbers in, even if it's a multiple choice question. You don't want to make a silly mistake. Here's our capital M for molarity, and we need moles per liter for molarity of the solution. Well, we weren't given moles. Sometimes you are, sometimes you're not. In this case, we have to do a first calculation, and here is moles is equal to mass over gram formula mass. Calcium chloride, the gram formula mass for CaCl2 is 111 grams per mole. If you're not given the gram formula mass, remember you want to list the elements. You want to put down the number of times they appear in the formula, the masses off the periodic table, multiply them out and add them up. First thing we're going to do here is the mole calculation. I'm going to do it right here on the side. I have a mass of 330 and a gram formula mass of 111. And when I go ahead and I divide, we're going to get the number of moles to be 2.97, which rounds to 3. 3 divided by, it's 1 liter. The answer is a 3 molar solution. We don't say 3 molarity solution, a 3 molar solution. For part B, The part is the mass of the solute, which is our 330 grams of calcium chloride, and that is divided by the whole thing. It's the grams of the solute plus the solvent, and in this case, the solution is already given. So the 1,000 grams has the 330 grams of solute already incorporated into it because the word here is solution. If we were told it's 1,000 grams of solvent, we would have to add the two numbers together. That is not the case. We put 1,000 then below, and don't forget times 100. Plugging it into the calculator, we get an answer of 33%. Same solution is a 3 molar solution, or 33% by mass. For the last one, it's going to be the mass of the solute again, which is the 330 grams over the 1,000 grams of solution. Now we're timesing by 1,000,000 instead, which is 10 to the 6. When we do that, we get an answer of 330,000 parts per million. Same solution, 3 different ways. Let's take a look at a few more. All right, for questions 1, 2, and 3, you'll notice in parentheses they tell you what type of solution concentration you're making, and then I put in parentheses the answers. You might want to set them up, calculate, and check your answer, and if not, come on back. I'm going to put the answers up myself right now. So pause the video, try them out for yourself. Alrighty, for number 1, my recommendation always with the math is you take the equation and you write it down. And since I have it above, I'm going to just leave it there. Not so great at writing it on the screen here. We need our part, which is the mass of the solute, which is the 25 grams of glucose. Now, for the whole thing, mass of solution, solute plus solvent. In other words, I got to take my 25 and I got to add 475. What goes in the denominator then is 500. And don't forget you're multiplying by 100. A lot of times on standardized tests, especially the New York State Regents exam, all they might ask for is the setup. What you see in front of you now is a good setup. But if you forgot the times 100, you're not going to get credit. All right, when you plug it in the calculator, you're going to get an answer of 5%. I put it as 5.00 if we're dealing with significant figures. For question 2, it's volume percent instead of mass percent, but it is still part over the whole thing times 100. The part being the the volume of the solute, which is going to be the 90 milliliters of the hydrogen peroxide. And in this case, now we got 3,000 milliliters of solution that also contains the 90 milliliters of the hydrogen peroxide. This times 100, and you're going to get an answer of 3%. For the last one, we're dealing with parts per million. We're going to go now, let me just get rid of this for a minute, and we're using the part per million equation instead. Same fraction, mass of solute, which is the part, over the mass of solution, which is the whole thing, but times 1,000,000. All right. The other thing that's tricky here in number 3, you have milligrams and you have grams. Well, let's change the milligrams to grams. And if you remember how to do that, there is 1,000 milligrams in 1 gram of water. If you slide the decimal, the King Henry's drunken uncle drinks chocolate milk, right? We are here at milli and we want to go to grams. I'm going to slide the decimal 3 spaces to the left. It's 0.002 grams, which represents the 2 milligrams, divided by the mass of the solution, which would be the 100 plus the 0.002. It's not going to be that significant, the 0.002, but I'm going to still put it here because if you're asked about a setup, you want to make sure you do everything perfect. So it's 100.002 grams now times 1,000,000. When you plug this in the calculator, you're going to get an answer of 20 parts per million. Awesome. Let's do a few more. Make sure we got this, and you're on your way. In question 4 here, we have a 2.5 gram sample of groundwater, and we have some copper 2 ions in solution, and we're looking at parts per million. The answer is here. You want to check it yourself. Pause the video, do the calculations. If you're getting the answers, you're getting it right, go for it. You just keep going. And if not, obviously you want to listen so that you get this right. Parts per million, of course, the part is going to be the solute, which is the 5.4 times 10 to the minus 6 grams of the copper ions over the whole thing, which is the 2.5, right? Because it's a sample of groundwater, it's going to have the copper ions in it. So 2.5 grams at the bottom, and then times a million because it's parts per million. When it comes to parts per million and percents, the only thing that's tough is just recognizing what you're putting in the denominator. All right, for question 5, you're dealing with molarity. Molarity is moles of solute, and luckily in this case they gave us the moles, so we don't have to convert, over liters of solution. Well, they gave us milliliters. We do have to convert there. We're back to sliding the decimal 3 spaces to the left. Look at King Henry if you have to, or remember that in 1 liter there's 1,000 milliliters. We got 0.161 divided by 0.310, and we should get the answer of a 0.519 molar solution. For number 6, now we're looking to solve for moles. Real simple. We're going to then plug in molarity, and moles is our quote-unquote X, right? And let's see, we got milliliters again, so we have to convert. We have 0.879, sorry about my drawing here, is X over, all right, I think it's 35.1, so it's going to be 0.0351 liters. When you multiply those two numbers together, you should get the answer of 0.0309. We have, I think, 3 left here. Let's get them done. Number 7, real straightforward. We're looking for percent by mass. We need the mass of the solute, which is our 5 grams, divided by the mass of solution. The 5 grams are built in, and multiplying by 100. In other words, it's going to be 5 over 100 times 100, and of course that gives us the answer of 5%. For number 8, we're looking for parts per million. We have 10 milligrams of lithium fluoride in 5,000 grams of solution. Well, the 10 milligrams is already incorporated, so for parts per million, we just have to change the 10 milligrams into grams. We're going from milli, we're going back, we're sliding 3 decimals to the left, so it's 0.01 over 5,000, and that's going to be times 1 million. The last one here in number 9 is also a parts per million question. The mass of the solute in this case is 20, and we got 40,000 grams of solution. That incorporates the mass of the solute since it's told to us that it's solution. And what are we doing? We're multiplying by 1,000,000 again. And you're going to get your answer. Boy, my zeros are pretty bad here. 500 parts per million. That ends this video on solution concentration. I hope you found this video helpful. I have more videos here on my YouTube channel, so check them out. Please subscribe, and as always, keep working hard, and good luck.